So, so yesterday we were studying this localization. So instead of so we're doing just the supersymmetric Chern-Simons theory. So instead of calculating, so let me actually now put the correct factor that I want to put. So this supersymmetric Chern-Simons, I'm going to take it as place A, which A plus interaction term. So this is, I guess we need to do some minus sign. And then we added this term here, so the supergeometric action, and this was the partition function that we wanted to add. And then we saw that actually this guy has all the properties to be a good perturbation in the localization method, in the sense that this Grassmann symmetry of the theory acting on a Grassmann quantity such that the bosonic part of this is positive definite, and actually it vanished at the locus A mu equals 0, sigma equal to a constant, sigma 0, and then the auxiliary field was set to be this quantity here. Okay? Now, if we want to actually compute this at equal to infinity, we have to be a little bit more careful. And the first thing you have to do is we still have to do a path integral in gauge theory, but we have to be very careful because this is a gauge theory. So gauge theories have a gauge symmetry, and you have to fix the gauge symmetry in order to get something useful. So we need some sort of gauge fixing here. And it can be, I mean, it's actually not very difficult to see that, well, gauge fixing means here adding ghosts and anti-ghosts, and it's very easy to see that this doesn't change the localization properties. It's localization in a gauge theory is compatible with gauge fixing. So the gauge fixing, here we have to choose a gauge. So we are on a 3-sphere, and we are going to use the covariant gauge mu equal to 0, or if you want, in terms of differential forms, I'm going to use that d dagger on A, where d dagger is up to a sign the standard Hermitian conjugate of the Drag operator. Now the gauge symmetry we have here, of course, is the fact that we can always shift A by dA of C, where C is a scalar. And the standard gauge fixing procedure, you have to add ghosts to the theory, so you have two ghosts. And the ghost axiom, you can actually write it schematically. I'm not going to give you all the details, but schematically something like E mu, I would say D mu, is A of C, something like that. So this is the schematically the ghost axiom. So let me call this ghost. So here, well, maybe I should write it like this. So
there's a C bar somewhere.
Yeah, sorry, there is a C bar here. Yes. So delta mu is the derivative covariant with respect to the spin connection. So this is and d mu is covariant derivative with respect to everything. Okay. So in particular here there is the standard in this gauge fixing action there is a vertex involving the ghost, anti-ghost, and the A coming from the covariant derivative here. Okay, so this is just to make sure that everything is done properly. So we have to add a ghost action here. And actually, there is already a simplification in the path integral due to this gauge fixing. And the reason is that when you fix the gauge here, you cannot integrate over possible one connections. So you have to decompose, one way of doing this is you decompose the connection in general as a exact form and a co-exact form. So you can always write A plus D phi plus A prime, where A prime satisfies this constraint here. So essentially this means that the gauge fixing means that this phi guy has to be put to 0. Okay? So essentially because this is exact, this is co-exact, and the fact that you have this constraint here, this gauge fixing means that A has to be co-exact, so essentially phi has to be put to 0. So when you do the path integral here, at the end of the day, let me write it in some detail here, what you will get is something of the following. You get the determinant, the prime determinant of the scalar Laplacian to minus 1/2. So this is an overall factor. Here we are computing the partition function. I have to be careful with overall factors. So this is coming from the change of variables from A to B prime. Again, the details are a little bit complicated and you can check them in my lectures. Let me just sketch what is the answer you get. Then you will get an integral of A prime. You will get an integral of the Gauss fields. And then you will get an integral over the rest of the fields here. So this comes from this Jacobian factor, and then you have this guy here. Okay, so that I got before. So this is the gauge fix path integral that we want to compute. And here everything now depends only on A prime. So we integrated out this phi here, and we eliminated that. So here this actually depends on A prime, and this also depends on A prime. So this is a technical detail, but it's good to keep it in mind. And now, what we are going to do, well, what we know now is that this gauge fixed path integral localizes in that local there. Okay? So we know that it localizes. So we want to do the path integral when t goes to infinity, hoping that it's going to be easier. Okay? Now, the way to do this in practice is the following. We are going to do this path integral. We know that the calculation of t goes to infinity is going to be fine. It's going to give me the same result. So what we're going to do is we're going to do the standard expansion of this path integral around a given configuration. And this configuration is going to be the configuration which it corresponds to the fixed point locus. So I'm going to do an expansion of this path integral around that configuration. So around A prime equals 0. And then I'm going to put sigma equal to sigma 0, and then I'm going to put, well, the other fields are going to be fluctuating around standard configurations. So in order to do that, I will, as I do it, as one does typically in the background field method, I'm going to actually divide the fields in fluctuating, on fixed backgrounds plus fluctuations. And very importantly, since I want to do now the path integral in a standard way, I want to get rid of this factor of t, not to have canonical kinetic terms, so I'm going to normalize my fluctuations in this way. So I'm going to actually do this. I'm going to put also d equal to minus c0 or plus 1 over the square root of t prime. And for the other fields, for example, the fields appearing here, also have non-canonical kinetic terms. I'm going to actually change this and normalize, redefine my fields in this way. So you could say, well, to introduce this t now, okay, to introduce this t because you wanted to go to t going to infinity and do the calculation this, and now you are getting rid of it but rescaling the fields. Yeah, but this is only for the kinetic term. Now what you can see after doing this is that when you expand this, I think the function around this configuration, you will get just the free part of the Lagrangian will be canonically normalized, and then every single interaction vertex will be suppressed by a factor of t. And this actually reveals the true nature of this localization method. What you get, yesterday I was writing the integral is equal to integral under localization locus, but I was not very precise about how how you should go do the calculation. In practice, the calculation has to be like this. You get only the free part of this functional, and every vertex is suppressed. So at the end of the day, you only do a one loop calculation. Okay? So let me be a little bit more precise about this. Now, the first thing is that, first of all, as usual, you have to evaluate this functional over this point in filter space where we are expanding, and then we have to calculate the fluctuations. You can see actually that this configuration is a solution of the equation of motion. So we are doing essentially we are doing the path integral around a particular solution of the equation of motion. The first thing you see then is that when you evaluate all this on this solution, everything is zero except for this factor here. And this you can easily see in this integral, in this functional, Chern-Simons, supersymmetric Chern-Simons functional, there was actually a term which was minus twice d sigma integrated over dCbx, and this guy is the only one that is non-zero when evaluated in this configuration. And this is actually very important. You can see that this gives me ik over 2 pi trace of sigma 0 squared, so evaluated at the fixed point. And then we have here the volume, so this is just, here we are evaluating this on the constant configuration. Sigma is sigma 0, B is minus sigma 0 over R, and I'm putting here, at the end of the day, I will put R equal 1. You can see that actually the conformal invariance of the theory is that there won't be any dependence on the radius, so I can always put R equal to 1, and then I get this in here. The volume of S3 comes from doing the integral here, and this is just 2 pi squared, and at the end of the day, I just get I chi pi trace of sigma 0 squared. So from the full action, the evaluation on this 6-point locus just gives me this term here. This is the only term surviving. And now I have to expand around this 6-point locus and analyze the action for the fluctuations. So what do you get? Well, so when you take this full action and you calculate it for the fluctuations, so you expand around this 6 point, what you will get is the following, schematically. Well, you get something like a standard free action for the fields. So, for example, you will get here A prime, then you actually change, A prime, I'm going to now call it A again, because it's clear that after base fixing, I only have to integrate over connections which are co-exact. And then we have something like this. So this is the Laplacian for one vectors, for vectors A. And then I will have, very importantly, here in the supersymmetry Yang-Mills, I have the sigma naught, the sigma field is coupled to the connection, right? There is a kinetic term of this form for the sigma field here in the Yang-Mills action. And this gives me a coupling which is again schematically of the form, well, I think there is a minus sign, but there is something like A times sigma naught squared. So you see that this is the quadratic part in A. There is like the standard Laplacian for the vectors, and then there is this kind of constant background, which you can think about this as a mass for the A field. And then you will have something similar for the gluon, for the gluinos. So we have the standard kinetic term, and then again the covariant derivative gives you some sort of mass term for this guy. But this guy also got a mass term from essentially from the fact that we have to do this conformal coupling. So this comes from the fact that this term is not there in the usual supersymmetry on R2 on R3. Actually, here there is an R that I put to 1. I use this some sort of mass term that goes to 0 when R goes to infinity. Okay, and then you have the standard kinetic terms for the other fields, kinetic terms for C, C prime, C bar. Then you will have the standard kinetic terms for C prime, which is the fluctuation. And then you have interaction terms But thanks to this rescaling I did, all these interaction terms are suppressed at least by 1 over square. So this is kind of the magic of localization in this language. So at the end of the day, I know that I can take to infinity, but if I take to infinity, my field theory becomes a free field theory in which I have a contribution, a weight for the integration which is coming from this field here, from evaluating the action on this fixed point locus. And then I just have quadratic terms for the fields. Now when I put everything together, what I get is that the partition function, when I evaluate it at infinity, should give given up to an overall factors, an integral. So I have to integrate over the zero mode of sigma. If you think about this guy, I have to integrate over the zero mode, and then I have to integrate over the fluctuations. Now the integral over the fluctuations gives me a determinant of a scalar operator, which eventually will cancel with this. So this is the only integral that remains. Now I have a measure for this guy, which was this thing that I was computing there. And now I can integrate out A and lambda, and you can also integrate out C and C bar. As I say, the integral over sigma prime, the integral over C and the C integrals over C bar eventually remove this overall factor here. And the only thing it remains is the determinants for the fluctuations of A and lambda. And then what I get is this. I get the determinant of these Laplacian on vectors plus schematically sigma 0 square, sigma minus 1/2, and then the determinant of again, here I'll leave the schematic. Now, here sigma 0 square is supposed to act as an adjoint, so this is the action of sigma 0 here acts in a general representation. So sigma 0 acts as a bracket, okay, or something. This is just a schematic, sorry, this is in the numerator. This is in the numerator. So let me write it like this. So here you have the determinant of I bar minus 1/2 plus I sigma naught, and the determinant of delta 1 plus sigma squared. Again, this is a little bit schematic, but the message is here, right? Here what I have is everything reduces now to an integral over a constant, so this is a constant permission matrix. Remember that this was a field in the representation, so it's a constant permission matrix. I have this kind of Gaussian weight with an imaginary weight here, and then I have these determinants computed in the background of this constant. So this is a kind of standard exercise, computing these determinants on a constant background field. And again, this can be computed using zeta function regularization. And the reason why this is easy to compute is, again, is something that I mentioned yesterday when we were considering the weak coupling analysis. What happens is that the spectrum of these operators on the 3D sphere is very explicitly known. So you can actually compute this by looking at the spectrum, putting it in here, you will have an infinite product, you regularize this infinite product with zeta function regularization, and then you get a function of sigma naught. Okay? Now, here sigma naught is a constant Hermitian matrix, but of course there is always, in this zero mode, there is a remaining, there is a residual gauge symmetry. So you have a constant gauge field, there is still this remaining gauge symmetry, which you can use, can be used to diagonalize. And you can see that this also integrates this. You can use this residual gauge symmetry to diagonalize. So if you want, once I'm in this zero mode sector, I can use my gauge symmetry to go to what is called the abelian gauge. I can just abelianize this thing. And at the end of the day, when everything clears out, well, you have to compute this. This is a non-trivial exercise. Again, I can tell you to look at my lectures in order to see how this is done in detail. And at the end of the day, you get something. So I'm going to write as follows. Let me change my variable to new. So the new here minus 1 over 2ds sigma mu I squared. So here I'm going to essentially write this as 1 over 2 pi after the analyzation mu 1 mu n. So I'm going to do this calculation for mu 1. So this is the measure of these guys here. And then I will have, it turns out that this can be evaluated pretty explicitly. And then what you get is a product change of mu I over 2 squared. Actually, this is, the way I'm writing it is very practical, but it's not very illuminating. This actually comes from a product over the positive roots. And it's actually, you know, remember that sigma 0 adds in the general representation, so it's diagonalized by acting on the root spaces. And then it's natural that this is going to involve at the end of the day a product of the roots, because this is the off-diagonal part of the Hermitian matrices are actually the action of the Eigen action on this off-diagonal part is essentially labeled by the roots. So at the end of the day, you will have a product of the roots. So this is the final result, and this is the path integral of supersymmetric Simons theorem. Okay. Evaluated, you see that it depends on n. Here, there is a dependence on n. And then, sorry, I didn't tell you what is this guy, which I like to introduce. Again, it is yet another coupling. It's useful in, it's just the inverse of k. So this is proportional ds. But we use it many times in these calculations, and I decided to call it here G topological. Now, this term is, of course, just this term. After you change this variable, after you diagonalize and everything, you have this term. So this is the answer. Okay? Now, this is the answer for the supersymmetric Chern-Simons matter. And as I told you the other day, this should be equal to the bosonic Chern-Simons theory. And actually, this integral can be done exclusively. It's a very nice exercise that I cannot propose it here. So, exercise. Use bi-determinant formula to calculate this integral.
Sorry, is there a van der Waals one there?
Sorry?
Van der Waals?
No, the van der Waals is already here. This thing, when the difference between eigenvalues is small, becomes the van der Waals. So actually, there is a van der Waals coming here which cancels out. This guy is not exactly this thing, it's this thing divided by the van der Waals, so at the end you get this. So it's already here to calculate the integral. Okay? And what you can see if you do this calculation is that this is exactly the partition function of bosonic Chern-Simons theorem. Okay? Up to overall normalization that you can actually fix with this calculation. Okay, so now let me very quickly tell you what happens if you include matter, because you know this already. I mean, I didn't give you all the details. I hope I gave you a more or less consistent flavor of how these calculations go. Let me tell you now, because I want to at least devote half an hour to actually calculating at the end of the day this matrix integral. This is trivial to calculate. This you can use by determinant formula to calculate it. So this is actually a sum of Gaussian integrals, so you can do it explicitly. Now, if we add matter, if we now add matter to the game, what you can see is you will get exactly the same type of integral, but with an extra factor here. So I'm going to consider just the simplest case, which is a self-conjugate representation. So if you have a self-conjugate representation, the contribution of a matter in this integral is just, let me write the thing in a sort of, so here, lambda are the weights of the representation. And you think about this as a weight acting on I mean, as a product of two weights. Okay. So, for example, let me just give you an example of this. An example which is important. If your representation is the bifundamental plus its conjugate, the weights of this representation, you can, so for example, if you have here two nodes, right, and then you have here a un1 and un2, and here you have a bifundamental representation. If you choose a basis for the weight space here, called A1, AI1, and here you choose AI2, the weight of the bifundamental representation, and you can do this, and if you choose the, I mean, you add, so this is for, so I'm adding this and its conjugate, so you get this. And then, you know, this is the product of these vectors which correspond to the weights with mu, and then what you get is the product of ij of twice cos of mu I minus mu j divided by, sorry, mu I minus lambda j. So let me call that. So here, and a little bit, I'm confusing a bit here because here there are two actually. So mu here I'm writing is as a vector mu for the first vector multiple. So this is in the Cartanic mode of un1, and actually adding another vector mu which is in the Cartanic of un2. So essentially here my gauge group is a product of two gauge group. So here I write also mu as a sum of the mu I1, and mu is the sum of mu I2. Okay? And assuming here, again for simplicity, that un is the same here. Just assuming ABN here. So this gives me one of the contributions that we get from matter for this thing. Okay. Now, here I'm introducing two vector. I mean, this is like in ABN theory. I need two nodes, so each node contributes with a factor of this. Okay, and the bifundamentals connecting the two nodes contribute with this factor. Okay, is this more or less clear? I have the feeling that I was a little bit too fast. So let me actually put everything together for here. So here we did a calculation for a single gauge group. So this is for a single gauge group. And you have two gauge groups like this. It's very easy to see. I mean, you just take the product of these two guys. So you have two gauge groups. You have un1, un, and un. Each node gives a contribution like this. So what you get at the end is the following. Actually, I need some space to write this. And this is going to give me the partition function of ABN theory. So you will have an integral over the constant matrix associated to one of the gauge nodes, one of the UN nodes. So remember that if you have UN single UN node, there is this field sigma 0. And this eventually gives you this factor here. Okay? So you have the mu I. Now, if you have another gauge group, you have just to repeat the calculation. At this level they are decoupled, and now you will have, I can actually write it like this now, let me just recover my standard notation. I will have sigma mu I squared, and for the other node, I think I actually forgot to say this, which is very important. The nodes of the two terms theory in ABN theory must have opposite levels. This is a condition for supersymmetry. So I don't know if I forgot to say this. Anyway, so you have a Chern theory with level k, a Chern theory with level minus k, and so we have to add. We just have to multiply these things. So we add this Gaussian term and the other. Now, you have this kind of product for the two gauge groups, mu I minus mu j over 2 squared, and then you will have the other term. So mu I minus mu j squared. And this is just coming from the gauge fields. Now, if you add the matter, you will have here these two fundamentals, and a similar calculation, and it gives you this final result there. So, since there are 4 in total, here this was a bifundamental plus a conjugate. Here, remember, we have 2 bifundamental with this conjugate, so I need the square of this. So, at the end of the day, you get mu I minus mu j. So this is the final result of the partition constant. You see, it's relatively complicated. So just let me summarize. So, well, here I did for the supersymmetry Simons. There is this fixed point, which we found yesterday by perturbing. Now we have to be a little bit more careful. We do a standard analysis in terms of background field method if you want. This is my background field, and then I do fluctuations around it. The fact that I can take t to infinity means that at the end of the day, I will have just a kind of free theory, and this is you get what you get at the end. This is just the value of the classical action at the fixed point, and these are just the fluctuations of the free fields around this background, and nothing else. And then playing a little bit with it, you eventually put this as a multidimensional matrix integral. Okay? And the matter, it's a similar story. You have essentially what you have to adhere now are determinants of the fluctuations of the matter fields around this configuration. And doing this gives you this sort of factor here. Never mind if in my notation was not completely consistent. At the end of the day, for a bifundamental and its conjugate, the important thing is that you get this kind of factor here. And this is the final result. Okay? So now you are in front of this matrix integral, and you can actually compute from here everything you want. One thing, the first thing you should do is to try to mimic perturbation theory of the gauge theory from this matrix integral. So do a perturbative expansion in 1 over k. Okay? This is actually quite easy. You can do it here, and then you check. For example, this is well. Let me first mention that this calculation, this result is due to Karpuskin, Millet, and Jakob. And one of the first things that they did in their paper was to actually check that perturbation theory for this matrix integral is actually giving you results which are compatible with what people obtain in doing perturbation theory directly in the gauge theory. Okay? Now what you have to do is solve this, calculate this guy in the regimes that we're interested. So there were 2 regimes. There were the M theory regime and the top regime. So what you have to do is to calculate this quantity at large n and fixed k, if you want to do the theory regime, or at fixed n over k, which is lambda, the top parameter, and large n. This is what you have to do. Okay? Now, what I'm going to do now is I'm going to do a calculation in the M theory regime, which will allow us to derive the result that I was telling you about. And the advantage of this method is that it's very elementary, only involves elementary statistical mechanics. So we can actually at the end get the right coefficient that I was telling you the other day. Okay. So let's do this. Well, I have to say that there have been various papers in actually calculating this matrix integral. So you see that localization solved half of the problem, because now we don't have to deal with the gauge theory, we just have to do with a matrix integral. But this matrix integral is still non-trivial. You have to find methods to extract the physical information from it. So there are like 3 different techniques to solve this matrix integral. Let me summarize for you how you do this. So there are 3 different techniques. One technique is just based on the top expansion. So you can look at this thing in the top expansion, and then you get so you have to have nk equal lambda fixed, and this is what allows you to compute the 0 of lambda. And this is something that we did with Drucker, so myself and my student Petrov last year. And this actually gives you these interpolating functions example. Okay? But this is complicated. It's It's a complicated calculation. It's a beautiful calculation, but it's complicated. I cannot explain this calculation in any reasonable way in half an hour. Now, after our paper appeared, actually you can compute all the FTs exactly at any ordering medium. Okay? Now, then for expansion, there were some papers by Herzog, Lebanov, more people, where they actually devise some sort of density functional theory, which is very beautiful. It's actually very powerful. So essentially, well, I will explain why I call this density functional theory. But it's only valid when, and it only gives you reliably the leading large n term, but at fixed scale. And then a couple of months ago, we introduced a Fermi gas approach. And essentially, this method of Hertzog can be regarded as a particular case of this. And with this, you can do actually the full 1 over n expansion at fixed scale. And it's actually very simple. And it involves like sort of elementary physics. So I'm going to this one. This I did with my students. And then I'm going to use this point of view in order to solve this matrix. Okay? So essentially, as we'll see, this kind of complicated quantity turns out to be the partition function of an ideal Fermi gas. And then, computing partition function of ideal Fermi gas is something that you should be able to do if you have taken a course in statistical mechanics. So this is what we're going to do. Okay. Okay, so how do we do this? Well, the only ingredient in order to use this Fermi gas approach is a non-trivial identity involving this complicated function. So this is a kind of more or less known identity. Let me write it here. And this identity allows you to essentially simplify the model very much. So this identity was used many times. For example, if you have worked out bosonization techniques in 2D conformality, it's an identity that appears sometimes. And it's an identity which tells you that this product there, so it tells you that mu I minus mu j over 2 times of mu I minus mu j over 2. So the square root of what is there twice cos of mu I minus mu j over 2 tells you that this can be written as a sum of determinants. And a sum of determinants is a sum of the permutations. So you take a sum of all possible permutations of n labels. You put the sign according to the symmetry of the permutation. And this is just the product of twice cos mu j mu I minus mu sigma I. This is actually a purely algebraic identity. Here it's written in terms of trigonometric functions that you can actually write it in terms of polynomials. This is a purely an algebraic identity. And now if you plug in this identity here and you message a little bit the result, not very much, and actually this messaging was done by these people in another paper, so there is a paper called non-perturbative checks of dualities where they do this messaging. So it's an elementary messaging, but if you want to see it, you can take this paper. At the end of the day, what you find is that this matrix integral can be written in a form which, after introducing all correct etc., in a form that might ring a bell. So first of all, this messaging actually removes these integrals, and you can actually do it, when you use this identity, you can do one of the integrals here, and then you will have only one single set of integrals. And then what you have here, I'm going to write it in this way. You have here a function, rho of x prime, which is essentially inherited from these trigonometric functions. And then you have x over k as now here, and this is the final expression to pay. Okay? So this looks still a mess, right? I mean, you have here a sum of permutations and so on, but if you teach statistical mechanics, which is my case, you recognize this as the partition function of an ideal Fermi gas. You have read, for example, the book of final statistical mechanics, you recognize this immediately as the partition function for Fermi gas. So let me actually review this. So this is actually quite elementary physics, but this is actually nice that at the end of the day this problem can be solved with elementary physics. And so how do you compute partition functions for ideal Fermi gases? Well, there are two formalisms. One is the standard formalism of occupation numbers, but you can also what you can do is to compute the density matrix of this system of n particles, and then if the particles are distinguishable, this is just take e to the minus beta h, where h is the Hamiltonian of the system, and this gives you the density matrix for a system of distinguishable particles. But if you want to calculate the density matrix for a system of undistinguishable particles with Fermi statistics, you have to anti-symmetrize with respect to one set of variables. So this is an standard result that if you want to calculate this density matrix, you start with the partition with the density matrix of the system of distinguishable particles, and then you sum over one set of permutations. So this is a standard formula in statistical mechanics. Okay, it's just applying the symmetrization principle to a set of Fermis. Now, if the particles are ideal, you have a system of of non-interacting particles, then the density matrix factorizes, and then what you get here is this kind of quantity. So this factorizes into pairs, and this guy here is the one particle density matrix. Now you want to calculate the partition function, you have to integrate, you have to take the trace of this operator. So you have to integrate over all of x1, xn, taking the x primes equal to the x's. Okay? So this is exactly the formula there. So you see that this formula is the partition function of an ideal Fermi gas, and this function here is telling you what is the one particle density matrix. Okay? So this looks encouraging. And now the question is, you have to identify here a Hamiltonian. You have to know just what the Hamiltonian is. Now, so when you want to interpret this as a Hamiltonian, and I have to say that here the temperature, the inverse temperature is just equal to 1. So let me put it like this. So you want to actually start a Hamiltonian from this. And this is actually quite easy to do, because if you have I mean, there are many ways of doing this. There is an easy way and there is a sophisticated way. But this is an exercise in, again, it's an exercise in one-dimensional quantum mechanics. What is the Hamiltonian that you get? And now, let me give you the answer. So if you think about this, just let me write rho the operator this, and then from that expression you see that this is equal to 1 minus 1 T of Q hat as an operator, and minus 1 T hat and hat Q hat, and U of Q is log of 2 cosh to the 2, and T is actually the same function but for 2. So this is the operator that you find, and very importantly, if you want this, I mean, we're doing quantum mechanics, so you have to actually introduce an H bar, And the way you introduce the H bar is to see that the natural way to do it is actually to have something that doesn't depend on the H bar. Hamiltonians usually, when written in terms of Q and P, do not depend on the H bar, and the way to actually make this is to put the H bar equal to 2 pi, to big K. Okay? Now, this Hamiltonian is not ordered in the right way. You cannot, if you want to identify this with e to the minus H bar, H hat, you said it's not ordered in the right way, and this is actually something that people who do lattice gauge theory, when you study transfer matrix, you see that this is the same kind of ordering problem that you find. So what this is telling you is that your Hamiltonian is actually given by UQ plus 2P plus simply H bar corrections, H bar squared. Okay. So if we are doing a semi-classical calculation, we can just restrict ourselves to this thing. So what is this kind of Hamiltonian? Well, again, if you're taking just the leading part, you see that this Hamiltonian has a kinetic part, which is given by this, and has a potential, a one-particle potential, which is given by this. So what you have, if you look at these quantities, this function is actually a function that asymptotically, so you see that UQ asymptotically goes like Q over 2, when Q is large, and the momentum, the kinetic function goes again like P over 2 when P is large. So if you have a system with very large energy, and in particular you have a system with many particles, most of the particles will have large energy, and then you see that what happens is that you have a system of particles that have just a standard ultra-relativistic dispersion relation. It's the kinetic term from an ultra-relativistic particle. And then these ultra-relativistic particles are sitting in a linearly confining potential. So this is what it is. So essentially, this part, so what you have are ultra-relativistic fermions in a linear confining potential. In a linearly confining. So this is actually a very simple system. And notice then that we mapped our problem. At the end of the day. So what we have found is that. So this is a last equivalent that I will use. So what we found is that ABN theory, which is a theory characterized by two coupling constants, is actually an ideal for the gas at the level of computing the partition function, and n is the number of particles, and h bar is just, and k is just related to the quantum mechanical h bar. Okay? So notice, for example, that now it's very easy to take large n, because large n is just the thermodynamic limit. The thermodynamic limit of a gas is what you actually do in statistical mechanics most of the time, so you don't need any special technology. And now, h bar is actually proportional to k. This is actually quite curious, because this means that the semi-classical limit of this gas is actually the strongly coupled string theory. So k, remember, was 1 over the string. So the semi-classical limit here is the strong coupling limit of type 2 theory. Okay. So in a sense, this system actually makes possible to calculate quantities in the strongly coupled limit of type 2 string theory. So essentially it's a dual description. Okay, now I'm going to do now a very simple calculation, and probably this is my last calculation for this object. Here. And okay, so if you have ever studied ideal gases, you know that the canonical partition function is not the right quantity to look at. The canonical partition function is a mess because you have all these another permutations. This is one way of seeing it. But what you do usually when you calculate partition functions of ideal gases, you go to the grand canonical ensemble. So you introduce then the grand canonical partition function, which is just summing overall canonical partition functions with some fugacity set. Z is the viscosity and to the mean. Okay. Now, so now the ground potential, these are again all the standard formulas, is of the log of psi, which is the ground partition function. Then here the number of particles is fluctuating. We have an average n, which you can compute as dg over mu. It's going to be an important formula later on. And if you compute this at large n, in the thermodynamic limit, all ensembles are equivalent, so you can compute the free energy as J of mu as a function of n, which you find from this equation, minus mu as a function of n times n. So this is again the standard Legendre transform that you use to calculate things to go from one ensemble to the other. Okay? Okay, so now what we want to do now is to calculate the ground potential of a Fermi gas in this potential. The Fermi gas with this ultra-relativistic in this linearly confining potential. So this is actually a very easy exercise. And the way to do this is actually using the standard occupation number formalism. So in occupation number formalism, you know that the number of particles is given by the integral, the all possible energies of the density of the state divided by the occupation number of a single fermion. Right? This is the occupation number for a fermion. This is the density of the states. So this is a formula that at least I teach my students of third year. So actually here what happens is that n very big means energy very big. And as we will see, it means mu very big. So when E and mu are very big, this is like having a small temperature in a system. Usually this is multiplied by beta. Taking low beta, small beta, is like taking low temperature is like taking very large mu. So this, in this thermodynamic limit, you will see that this assumption is consistent, can be computed as a zero temperature Fermi gas. So a zero temperature Fermi gas is just this. And this is just what? This is just the number, this is the volume of the Fermi surface. So, as we will see, this is actually a good approximation of large n. Now, what is, so n, if you want, this is the number, so n of mu is the volume, is actually the volume of the Fermi surface divided by 2 pi h bar. So it's the volume of phase space divided by 2 pi h bar. This is the standard calculation that we do. I mean, if you want to do a semi-classical calculation, what you do is you suppose that the phase space is divided into cells of size 2 pi h bar, and then you put one fermion in each cell until you get to the end of the Fermi sea. And what is the Fermi surface here? Well, the Fermi surface is just given by h equal to mu, is this equation. And this is an equation which is pi over 2 at large energies. You can go to Q and P large, is equal to this. So, so here, if you draw this, you see that the Fermi surface of this system is a square, like a losange, like this, and this is mu. So this is the phase space. This is P. This is Q. This is 2 mu. This is 2 mu. This is 2 mu. And this is plus mu. So we're almost there. So you see that n of mu is just the volume of phase space, which is h mu squared divided by 2 pi h bar. Okay? So this is then n. Okay? Sorry, so the 2 pi h bar, but remember that 2 pi h bar is 2 pi k, so I get my final equation mu of mu is actually 2 mu squared over pi squared k. Now with this we can do everything now. Okay, so this is trivial, right? This is the area of this square. So we can do everything now. You know, just go to this equation there. Just go to these equations. And, well, first of all, you notice that mu is actually pi square root of nk over 2. And then this is my assumption that mu is, when n is large, mu is large, is actually consistent. Mu is proportional to the square root of n. And now j of mu, the easiest way to calculate this is just by integrating this relationship. And then if you integrate there, you get 2/3 of mu cubed divided by pi squared k. This is a trivial integration. And now we can calculate f. What is f? Well, f is j of mu, so it's 2/3 of divided by pi squared k, and then mu to the cube. But mu to the cube, you see, is n to the 3 halves, k to the 3 halves, divided by 2 to the 3 halves, and then you have a pi cube. And then you have to subtract this part there, and this gives pi to the square root of 2. K to 3 halves, k to 1 half, and then this gives you minus square root of pi over 3, k to the 3 halves, k to 1 half. This is exactly the quantity that we obtained yesterday using the Riemann, this Einstein reaction, including the right half. So you see, this is the simplest possible derivation of this n to the 3 halves behavior, including the right coefficient. And now this behavior is completely demystified, because this is the scaling on n that you find if you have a one-dimensional system of fermions in a linearly confining potential. So actually, when you do progress with fermions with different potentials, you find all kinds of scalings with n. And n to the 3 halves is just the scaling that you have when the dispersion relation is linear in P and the confining potential is linear in Q. So this is completely straightforward. And then, well, there are more things that you can do. And the nice thing is that, well, this is an ideal gas, so you can compute H-bar corrections if you want. And it's a kind of easy, it's a beautiful exercise in semi-classical calculation with statistical mechanics to do this. And then you can, I mean, here I made many approximations, so you can probably say that, you know, that I should be able to justify them better, but actually you can do a calculation with no approximations. Only what you get is this is the first term, then you get mu of 1 over 3k plus k over 24. So this is a subleading correction in n, because the leading correction is mu. Remember that mu is proportional to 1/2, so this is subleading in n, this is subleading in h bar. Then there is a constant with a function of k, and then there are exponentially small corrections. So this is the exact answer. When you actually use this answer to calculate the free energy, well, this is again an approximate function. This is remember that the Legendre transform in statistical mechanics is obtained by the saddle point evaluation of an inverse integral. So you can actually see that if you use the whole machinery with no approximations, what you find is that the free energy of ABN theory is the log of an AB function. And then you have this kind of and then you have corrections which are of order square root of n over k. So they are exponentially more corrections. So the beautiful aspect of this formula you can find again with this formula is that this gives you the full 1 over n expansion of the partition function of ABN theory at fixed scale. Okay, so this is the full n theory partition function at all orders 1 over n. And in particular, this is the full partition function of 11-dimensional supergravity at all orders in the Planck constant. At at least in the perturbative expansion in NP over L. Okay? This is it. It's an AD function. Okay? Now there are non-perturbative corrections, which go like e to the minus NP over L, but this resounds the full. So for example, this makes predictions for all possible quantum corrections in supergravity at 1 loop, 2 loops, etc. in this expansion. Okay? So this is just everything is encoded here. Okay, so I'm already over time. So maybe my last comment is that you can also do a calculation in the top limit. Let me just give me 1 minute. So if you do a calculation in the top limit, you actually get something very similar. I mean, the two calculations are overlap, not completely, but overlap partially. And the partial overlap actually makes possible to calculate this. Yeah. So this in the top limit, you can these are certainly our original calculation, and what you find is that this is minus pi square root of 2 over 3 lambda minus 1 over 24 to the 3 halves k squared plus corrections which are now also exponentially n but different. So you can see now that this formula and this formula, you can see that they agree up to this factor of 1 over 3k, which is not taken into account here because it's actually here this is a genus 1 correction, it's a correction in, so this is after around 10. And the interesting thing is the nature of the exponentially small corrections. Actually, if you look at this is my last sentence today. This, if you look at this, and you use the M-theory dictionary, which is the one that you should use here, because this is large n and k fixed, you find that this exponent is a cubic exponent. So this is the area, this is the volume of a three-dimensional object. So this will be interpreted as membrane corrections in M-theory. Okay? Now here, on the contrary, if you use the type 2A dictionary, what you find is that this exponent is of order L over Ls squared corrections. So this is a two-dimensional object, not a two-dimensional object in type 2A theory, so this is a worship instant. So here we have membrane instantons, and here we have worship instantons. And I have to say that both are explicitly calculable in this context. So you not only get the leading supergravity approximation, but all perturbative corrections in supergravity, in the expansion of the Planck constant, and you even get membrane corrections. Okay? From membranes wrapping 3 cycles in S7 mod ZK. So for example, there is an S3, this is an S7, and this is what this guy is wrapping. Okay? So, okay, I think I finish here. So, I think the goal is more or less fulfilled in the sense that we were able to check this central three halves behavior. So we did the calculation yesterday using gravity. It's a very simple calculation. And here, after all the dust settles, you can actually use very elementary physics to derive the same thing, and we check the coefficients. So here is actually one very sharp and beautiful test of ADS-CFT. You have a prediction from gravity, non-trivial number, and then you have checked it. You can check it actually in the ADS calculation. And this is for ABJM, but this check has been made for many N equals 3 supersymmetric subatomic matter theories using the same techniques. You can do both. And we have now a full family of tests of this ADS for CFT theories. Okay? And the key ingredient again is localization. So let me finish here. Please.
So I know that localization has been applied in the supergravity context. Do you think there's a chance that at least the large N versions of these results could be gotten from supergravity localization?
Well, for example, you want to do this worst instant calculation, it's likely that there is a way to do this using localization directly in the superstring theory. In a sense, that's the way it should be done. But I don't know how it would go. We would have to try to implement this supersymmetric degrees or formalism, something like that, and then try to get this. But it's true that there is some asymmetry, in the sense that the gauge theory calculations have been done using localization, while the string theory calculations are usually done by brute force. So there should be some improvement on that side. But in principle, this thing can be computed a priori by doing a semi-classical calculation of a Green-Suarez string, which is like what people do when they look at the spinning strings, right? They look at non-trivial configuration of the classical string. They do fluctuations around it, and they get, for example, the first one loop fluctuation, and then they get something. Here you should be able to do the same thing. The only thing is that the semi-classical configuration is not a spinning string, it's a Walsh instant. So it's a extended string wrapping a cycle. But the principle of the calculation should be similar. But of course, it would be great that one can actually use localization here.
Marcus, all this was made possible with great effort and very nice techniques.
Yes.
Because you were able to compute the spectrum of certain operators like this Dirac operator.
Oh, yeah. Yes.
You knew the exact spectrum, and then you could use it as regularization and find the expression for the sums. Is there some geometric deformation, some additional parameter you can introduce in these backgrounds so that still this spectra are computable? And you have, apart from volume moduli at the end, you have additional moduli.
There is this, people have done a lot of computation, what is called the squash 3 sphere.
That's what
so you deform geometrically the 3 sphere with this parameter. We did have this extra parameter, and then still everything can be computed. And at the end of the day, in this determinant that they wrote here, you will have a more complicated function involving this parameter b. And there was a lot of activity of people, looking also for the gravity dual and comparing partition functions.
But this is still an open problem. I mean, what is the physical interpretation of this quotient parameter in that case, the shape modulus?
Well, I don't know what is the interpretation in supergravity. There were some recent papers on this that I haven't really read in detail. But, these are deformations which can be implemented in ABS-CFT, and you can run the whole thing. Other thing you can do, which has not been done, is to, instead of doing the calculation with a string, say doing it on a cipher manifold, as Johan was explaining to us how to do localization of pure transitions on a cipher manifold, where now if you do this in the full ADM theory, then you will have a complicated path integral, and then this should be dual to ADS. An ADS background where the boundary is no longer an S3, but is some sort of deformation of S3. So that has not been explored.
So if somebody wants to look a little bit further at this literature, but is not very knowledgeable about that part of the literature like me, what are the papers that you would recommend for a state of analysis?
Well, as I said, I wrote these lectures, and at the end of the lectures there is a summary of what is going on in the literature. But this we have been developing. So there is like in the last chapter of my lectures is like a review of the existing literature in March or in April. Okay? So now things have changed a little bit, but you can just click there for you can just see what people did.